All right, in this last example, example 5, we have the folium of Descartes, which is apparently this implicitly defined curve given by the equation x cubed plus y cubed equals 3xy. And we're supposed to find all the non-zero points on this graph which have horizontal tangent lines. Okay, so, and there's a hint here. So the first thing is we need to know how are we going to find this. So what does it mean to be a horizontal line? Well, it means that your slope is 0. And if we want this to be a tangent line, then we know that we're going to find the slope via the derivative. So ultimately, we want to find all non-zero points that satisfy dy dx equals 0. Okay, so we have a roadmap for our solution. First, we're going to find dy dx by taking our equation and differentiating with respect to x on each side. Oops, differentiate. So let's go ahead and do that. So on the left-hand side, we'll have 3x squared plus 3y squared. And then since we just differentiated a y term with respect to an x, we'll tack on a dy dx. The right-hand side, we have a product rule. So we'll go ahead and treat 3x as the first function and y as the second function. So the derivative of the first, so the derivative of 3x is 3 times y left alone plus 3x left alone times the derivative of y, which is dy dx. Okay. Now, unlike the previous examples where we were given a point and then we had to find the slope, it's sort of the opposite. Now we have the slope and we want to find the points. So we can go ahead and we can set dy dx equal to 0 because we know the slope has to be a horizontal line. When we do that, this equation simplifies dramatically. This should simplify into, let's see here, 3x squared equals 3y. So we get y equals x squared if we divide by 3. So this right here, y equals x squared, certainly isn't a point. This is an infinite number of points. It's a collection of points. It's all the points that live on this parabola. Okay, well, how do we reconcile this? What does this mean? Well, all this equation means is wherever dy dx is equal to 0, this must be true. Okay? But here's the thing. Are all of the points that are on this parabola, are all of them the same points that are on here? Absolutely not. The parabola is probably something like this. Ooh, if I were a better artist. Something like that. So clearly not all of the points that satisfy this equation satisfy this equation. But because we're only looking for points that live here, that means we have to see if are there any points that live on the folium that also live on this equation. So we can go ahead and find the intersection. Of this parabola with the folium. Now, how would we do that? Well, take one of your equations and somehow import it into the other equation, or set them equal. We can't set these things equal to one another because this equation's not solved for y and it's not solved for an x squared. But because this equation's solved for y, we could just replace the y's in the folium's equation with x squared and go from there. So that's what we'll do. So we'll have x cubed plus y cubed, and of course y cubed, of course y we're replacing with x squared, equals 3xy, so we'll replace that last y with an x squared. All right, and then we'll just simplify, collect like terms. So it looks like we have 6x minus 2x cubed equals 0. Factor out an x cubed, and we'll be left over with x cubed minus 2 equals 0 times x cubed. So then, of course, here we can just set each term of this product, there are two terms, set them equal to 0 and solve. So the first term, set equal to 0, yields us the solution x equals 0. And the second term here yields us with the cube root of 2. Now, this question specified that we're looking for non-zero points. So although this does satisfy this equation and the Folium's equation, it does not satisfy the additional constraint that we were not looking for 0 points. So I'm just going to go ahead and say that this is like irrelevant for us. So this cube root of 2 is the correct answer.